welcome everyone to from a grey and miserable Perth. I'd like to start with a few acknowledgements. First of all, Justin Drummond, who recently, several years ago, finished a PhD on palaeochannel deposits of WA, and several ex-colleagues at Deep Yellow, Jean-Christophe Corbin, Dave Prinsep, Alex Otto, and lastly, Judith Kinnaird, who used to be at Wits University in South Africa, whose students have done some key research on this style of deposit. But I want to start with some background, naturally enough. Nuclear is key to the green energy transition, I believe. Many countries believe. Unfortunately, Australia doesn't, but that's a different story. So currently, uranium consumption is running at the rate of 60,000 tonnes, which is the equivalent of 2 large uranium deposits being consumed every year to keep the world's nuclear energy operating. Supply, however, is dwindling, and it's currently less than 50,000 tonnes per annum. And it doesn't take a genius to predict an ongoing uranium supply deficit. And what this means is that there is a need for the discovery of more uranium deposits in general. The problem, however, is that since the 1980s, I think it's fair to say, there's been a paucity of research into most uranium deposits, with the exception of unconformity types, particularly those in the Athabasca Basin of Canada, and the Chinese, who have researched a lot of different deposits. And I want to digress for a moment and show you this slide, which is the Beijing Research Institute of Uranium Geology. I was fortunate enough to visit this place some years ago to give some lectures, and I was staggered to find that the institute employs over 5,000 people and has more analytical equipment than most earth science departments in Australia combined. So it's a pretty serious statement, I think, of the degree to which the Chinese value their nuclear industry and exploration for uranium in particular. It's a pity Australia hasn't taken a leaf out of that book. If we look at the industry as a whole, there are currently 442, well, I say currently, as of January 2021, 442 commercial nuclear reactors operating around the world in 31 different countries. And a statistic that surprised me is that there at that time, only 2 years ago, there were 52 reactors under construction. Hence the suggestion, excuse me, hence the suggestion that we might be heading into a severe supply-demand imbalance. During the period 2019 to 2020, 11 reactors were connected to the grid. Construction started on a further 8 reactors, and 14 permanently shut down. Positive developments for the industry have been announcements by the Biden administration of unequivocal support for nuclear energy and pumping billions of dollars over the next few years into promoting it. Another major fillip for the industry has been Japan's decision to restart most of its idling fleet, except for about 5 reactors, which were decommissioned soon after the Fukushima debacle. So all in all, I think it's a pretty positive outlook for the nuclear industry. Let's look at production now, and here's the top 5 uranium producers in 2020. Kazakhstan, head and shoulders above the rest, producing something like 40% of the world's uranium, mainly from in situ recovery methods. So it's a reasonably environmentally benign method of exploitation. Followed in second place by Australia, and at least half of that bar is made up of production from Olympic Dam. Third place is Namibia, which we'll be talking about in this presentation. The 2 mines active in Namibia both exploit so-called Alaskite deposits, which is really another way of saying Luca granite pegmatite. But they are both massive mines, Rossing and Husab. Rossing being, I think, the world's oldest continuously operating uranium mine. And then you have Canada and Niger trailing in 4th and 5th place. So 47,000 tonnes produced in 2020. Now let's turn to the subject of this presentation, which is paleochannel hosted uranium. It's also, this style of deposit is also known as surficial in the IAEA terminology. You might also have heard of it as calcrete hosted. And what you see in this map here is the distribution of most of the world's known examples. You can see they're fairly widespread. They're known on every continent. But the key thing to note here is that the occurrence is restricted pretty much entirely to Köppen-Geiger's BWH climatic zone of hot arid deserts. So there's a very strong correlation between the occurrence of this deposit style and hot arid conditions. The 2 biggest deposits are here in Western Australia. It's only a few hundred kilometres from those of us who are sitting here in Perth. But the only one of these deposits to have achieved production is Langer Heinrich, which is situated in Namibia, in that red dashed circle you can see on the map there. So on the next slide, you can see the grade tonnage relationships for the deposit group. In the inset, you can see all uranium deposits shown as the pink dots. And the red squares obviously show the paleochannel hosted deposits. So 2 key takeaway messages from these illustrations is that the paleochannel deposits can be extremely large, amongst the largest uranium deposits on the planet, but they are typically very low grade in the hundreds of parts per million. In fact, if you look at the big football at the top left, which is the Maranika deposit, the average grade of that deposit is 96 parts per million, which is extraordinarily low. It's little more than a geochemical anomaly. So that's the characteristic grade tonnage of these deposits. Well, let's look at, this is a satellite image, a Google Earth image, I believe, of the Erongo district in Namibia. And you can see from the inset, those of you who don't know where Namibia is, it's in southern Africa, next to Botswana and South Africa. What I've shown on this image is a combination of, in the solid lines, the current ephemeral drainage, including the major rivers, the Swakop, Khan, Omaruru, and Kwiseb. Now these are vast drainages, but they only flow once every 4 or 5 years, if that. Then within the basin, the overall area, there are a number of paleochannels, which are shown here in the dotted blue. They correspond in part to the current drainage, but they don't necessarily correlate exactly to where the current drainage is. These channels have been mapped quite effectively with airborne EM and by drilling. And you'll see the red is the uranium. There's a number of deposits here. You can see in the table on the right the individual deposits and their grade and tonnage. But the ones I'm going to focus on, particularly in this talk, are Langer Heinrich, and just below it to the south, the Tubus system. It's really effectively one large mineralized body that extends over 50 kilometers. So I'm going to refer to that as Tubus. And just to emphasize the point about size, if you look at the table on the right, look at Langer Heinrich, that has a resource of 170 million pounds, which is around about 60 to 70 million tons of U3O8. And that's equivalent to about 2 years of annual consumption. Right, now you should be looking at a rather picturesque slide. This is what the locals refer to as the moonscape, for obvious reasons. It's situated about a half-an-hour drive out of Swakopmund, and busloads of tourists turn up to watch this, to look at this every day. Well, what I want to show you this is, it really, I think, summarizes the Cenozoic and, the Cretaceous and later evolution of this area. And what you see in the center of the image, in the dark, is the metamorphic and igneous rocks of the Damaran, the Proterozoic to early Cambrian Damaran orogeny. Now, these rocks were denuded. There was a massive episode of erosion towards the end of the Cretaceous, presumably driven by a period of extreme rainfall, and that resulted in the formation of an unconformity known as the Namib unconformity surface, or NUS. And that unconformity surface was then buried by tertiary and younger sediments. And what you see in the middle of this image, forming the bulk of the moonscape, is pretty close to what that Cretaceous surface would have looked like. It's highly irregular, with some pretty major channels cut through it. The biggest channel in this particular case is down to the Swakop and Khan rivers. And then in the foreground, you see a remnant of the tertiary cover, which itself has been incised and eroded by more recent, probably current drainages. But just to finish off the story, there's the material you can see right at the foreground forms a thin crust of gypcrete, which is more or less ubiquitous over the area. So this gives you a bit of an indication of the setting, one of great climatic fluctuations from an early period of scouring, denudation, erosion, to the whole surface being filled up as the climate aridifies and this surficial flow dries up. That's the environment into which the uranium was placed. But just to reinforce that, here's an example of one of these palaeochannels that's had its paleo fill, its channel fill eroded. That's a typical example of the channel profile. This particular outcrop happens to be the Etango uranium deposit. It's an alaskitic style of thing. It's a Luca granite hosted deposit. And if you have a look at the rocks outcropping to the left, you'll see layers of white and these are layers of leucogranite, which are highly radioactive, carrying several hundred ppm uranium. Not hard to see how that uranium could then be eroded from the source and incorporated into the palaeochannel. So the place where the channel fill is best preserved is along the Quiseb River, which I've outlined here in a red box. There's no one place where the complete sequence is preserved. So it's a case of trying to stick it together from isolated outcrops along the flanks of the river. And what you have is a sequence of about 300 meters of tertiary through to Pleistocene material. In itself, demonstrating quite substantial climatic fluctuations from the Sondab sandstone at the base, which is a dune sand with some pliers, growing up into the conglomerates of the Carpen Cliff conglomerate. At the top of the Carpen Cliff, at the top of the Miocene, is a prominent calcreted layer. It's called the Camberg calcrete. And this layer can be recognized all through the district. It was then eroded and incorporated into the Ostwater conglomerate above it, which is terminated by another carbonate forming event, which produced significant tufa and travertine. The point I want to make here is that there's clearly multiple events of carbonate cementation, probably relating to small-scale climatic fluctuation. And as you go right up to the top into the Pleistocene, you start to see more marine influence coming in, and marine silts deposited close to the coast. Now, where does the uranium fit into this? It's a bit hard to correlate sediments that occur in the palaeochannels with this particular sequence, but my suspicion is that the Carpen Cliff conglomerate is the rock that hosts the bulk of the uranium, possibly close to its contact with the Camberg calcrete. Now, in this slide, we're looking at the Langer-Heinrich mine. Remember, this is the largest example of, the only example of this style of deposit which has been successfully mined. The host channel runs from left to right. In the middle of the image, you can see outcrops of the Damaran metamorphic rocks. And another point of interest, and again a digression, but the fog that you can see off to the right of the image is fairly characteristic of this part of the world. Swakopmund, in fact, is one of the world's foggiest towns, with almost 200 days of fog every year. It's also thought that the fog is responsible for carrying sulfur into the area off the ocean and producing the calcrete crusts that I mentioned earlier. Now, in this slide, we're looking at a three-dimensional representation of Langer-Heinrich. We're looking to the northeast, and there's probably about a 10 times vertical exaggeration. But the key thing to notice is we have a current drainage running through the middle. That's the pale yellow to white material. And beneath that, exposed as a number of outliers, and also on the flanks of the valley, are the paleochannel sediments of the Langer-Heinrich formation. And it's these which host the uranium at Langer-Heinrich. I also want to draw your attention to where it says hard pan calcrete up to the right of this 3D image. And this is clearly at a much higher level than the deposit. So this is a remnant of a calcrete sheet which has been incised and largely removed by the current drainage. The other thing to note is the presence of the blood-copied granite at the at the upper end of the channel. This granite is believed by many to be the source of the uranium which ultimately was deposited at Langer. And I'll talk a bit more about that later, because I think there's some alternative possibilities there. And these dashed lines I've just put up there just show you where the open pits are located. So a very long, very skinny open pit. Here's another view of Langer Heinrich, but this time we're looking from the northeast to the southwest. You can see in the middle the tailings retention facility, and the Heinrich deposit itself is barely visible in the distance. But what I wanted to show you here, just to emphasize a point I made previously, is here is an old calcrete surface on either side of the image. And that's been incised by active contemporary drainage. Now, that's had a couple of effects. One is the important effect that late incision has allowed the discovery of the deposit, because it's allowed what otherwise would have been buried to be exposed and to be detected by airborne radiometric surveys. The other thing it's done is almost certainly caused some of the deposit to be eroded away and moved probably into the sea. So this is a fundamental difference between the deposits of Namibia and the deposits of Western Australia. The latter being very probably are currently still forming. And here's a slide just to illustrate the point about the open pit at Langer being a very, very long, skinny thing. In fact, it's over 4 kilometers long, which is pretty much what you'd expect if you were mining a river channel. And in the background is the hill that gave the deposit its name. It's Langer Heinrich Mountain, composed mainly of quartzite. Now, moving down the scale, this is an example of the mineralization at Langer Heinrich. To give you an idea of scale, in the center of the image is a black box, which for those of you who are familiar is a radii, but for those of you who aren't, it's about the size of your fist. You can see a lot of pebbles. So this rock is best described as a pebbly sandstone, and it's strongly carbonate cemented. What you can see in terms of mineralization is the yellow stain, a very erratically distributed yellow stain, and that's carnotite, that's a uranium vanadate, and that's what makes up a substantial portion of the Langer mineralization. Although having said that, there quite remarkably have been no modern mineralogical studies of this deposit, as far as I'm aware, apart from one minor one, which demonstrated that there's also this odd sounding mineral thioumenite, which is a calcium end member of the vanadate series. Now, zooming in again, this illustrates another feature of the Langer ore, and in fact, palaeochannel ore in general, I believe, is that you'll see a lot of black fragments in this mineralization, and they are black quartz, very distinctive. And I'll talk more about black quartz shortly, but mine geologists have noticed a strong correlation between high grades of uranium and high abundance of black quartz. So one would assume that there is some sort of causal relationship there. Here's another example of the ore. This is a particularly high-grade example. This is from the Tumus deposit, which I'll talk about in a minute, in which the matrix has been almost completely replaced by uranium validates. Quite a spectacular sample, in fact. Now, although most of the mineralization is contained within the palaeochannel, there's a significant amount that occurs in the basement rocks underneath. And here you'll see in this image 3 fine examples of carnotite occurring along fractures in the basement. It's almost like somebody took a paintbrush and a jar of paint and painted this stuff on. It's really quite impressive. You also see the unconformity between the basement and the overlying palaeochannel. Now, I want to move on to the tumus deposit, tumus deposits. And here we're looking at an airborne EM image, a conductance image. This is a survey flown in 2008, more recently reprocessed by resource potentials. And what you can see here, I think you can see the outlines of the palaeochannel in the dashed yellow, but you can see the strong relationship between high conductivities or high conductance and the presence of these palaeochannels. And that's a very valuable way to map these things. And the reason for that, that increased conductivity is likely to be saline waters. But you also notice that as you get upstream towards the to the right, the response dies away somewhat, and that's probably partly due to the relative thinness of the channels as you go upstream, but also the fact that the palaeochannel sediments are charged with meteoric waters of low salinity rather than the more saline waters you encounter further down. And this is zooming in on the western side, just to give you a bit of a cartoon-like image of the geology of the tumus deposits. You can see the contours to channel depth, that they're ranging from 5 down to over 80 meters. So just to emphasize that point I made previously, the channel is quite shallow to the east, less than 5 in places, but increases substantially to over 80 to as much as 100 meters as you move further to the west. And this is what tumus looks like at surface. You can see a couple of little hillocks in the distance, which represent the remnants of the Damaran basement rocks. But the bulk of the channel in this location has been completely buried by Cenozoic material. So it's a different scenario here to Langer. At Langer, the evidence for post-ore incision was fairly prominent. Here, we're not seeing much of that at all. And this is a section from tumus, oriented north to the left. You can see the basement contact is somewhat irregular. That's fairly typical. Then you've got a sequence of fairly chaotically sorted and bedded conglomerates, pebbly sands, etc., capped by a layer of gypsum and basanite cemented conglomerate with a thin veneer at the top of pebbly sands. And these pebbly sands relate to the current ephemeral drainage system. Note while the occurrence of calcrete is hard to define within these channels, and it's rare to actually log the volume of calcite, I think one can say in general that the most intense sedimentation occurs towards the top, and that the mineralization is either in the most intensely carbonate cemented portions or immediately below it. So there is a link spatially between uranium and calcite, although I emphasize the fact that these palaeochannels are carbonated in their entirety over vast distances, whereas the occurrence of uranium is much more restricted, and that's something a mineral systems model needs to explain. And perhaps some way towards the explanation lies in looking at the detail, the petrography of the host rocks. This is an SEM image from a TEMA, and quite clearly shows detrital quartz, feldspars, and some heavy minerals probably derived from granites, almost certainly derived from granites, in fact, floating in a matrix of calcite with a bit of dolomite, but mainly calcite. But the uranium, which occurs as the yellow pixels, is clearly associated with the clays in green, and clearly, I think it's absolutely unambiguous in this sample, postdates the calcite. So calcite was there first, and by whatever process, uranium was introduced subsequently and occupied the interstices between the early calcite cement. So what are those clay minerals? Well, there's a range of different clays that have been identified. But if we go to the next slide, in figure A, which is an SEM image, you can see sepiolite, the characteristic fibrous form, and on the right in the figure B, we're looking at palaeochannels, both of which are magnesium-rich clays. A couple of the figures on the bottom I've borrowed from Justin Drummond. Justin showed that the carnotite is not only related to magnesium clay minerals, but also to dolomite, as you can see in figure C, and amorphous magnesium silicate, which you can see down the bottom there. So what does this mean for depositional process? I think most people who have studied these deposits over the years would fundamentally agree that the driver for uranium precipitation is evaporation, and some of the many chemical processes that go along with evaporation. And what I'll show you here is an example from WA rather than from Namibia, but it illustrates the point rather more clearly, I think. And you've got a salt lake in the middle, which is Lake Way. You can probably just about make out Wilde to the north of the Lake Way deposit rather than Lake Way itself. You can see the two uranium deposits of Lake Way and Centipede sitting right on the edge of the lake, and then the Dawson-Hinkler deposits in a paleochannel which feeds into the lake. Now, as I said earlier, I think the WA deposits are probably still forming. There's certainly no evidence of the wholesale dissection and erosion that we see at Langer Heinrich. So we can look at the waters there and the groundwaters and use the principle of uniformitarianism and perhaps suggest that these might be what was causing the mineralization in Namibia. Now, these waters are hypersaline. They trend from calcium-rich to magnesium-rich as you approach the ultimate source of evaporation in Lake Way. You also see a change from low pH to high pH. And as those waters come into the lake, they're pretty close or oversaturated with regard to uranium. In the Orongo district, the groundwaters tend to be low salinity, significantly uranium undersaturated, and I suspect that these are post-mineralization, probably more effective at removing uranium and redepositing it rather than being the smoking gun, the ore-forming fluid. And here's an activity plot from Justin Drummond et al. Just to underline some of these points, it shows pH on the bottom axis and the activity ratio of magnesium to calcium on the vertical axis. You can see that calcite and dolomite tend to form in intermediate pH regions, or let's say neutral to alkaline pH regions. But as you start to ramp up the magnesium content and as you move into more alkaline pHs, you start to generate palygorskite and sepiolite, and this mirrors pretty much what we see in nature. And this red arrow that I've put in here is the sort of trajectory that you might expect in an evaporation trend. What's actually driving the change in pH is probably the exsolution of CO2 from an ever-increasing hypersaline brine. So that's all I wanted to say about the depositional side of things. I just want to devote a few slides to source. And here's a map showing the granites in the headwaters of Langer and Tumas. To cut a long story short, the most likely source here is the Donkerhoek granite. But if you look at the table on the right, it has a uranium content of 3. So that's not a particularly attractive level. I personally think the most likely source is in uranium-enriched pegmatites, such as the one you see on the screen here, which is typical of what you get in the elastic deposits of the region. Could they occur at Langer-Heinrich? Well, yes. Geological mapping shows lots of pegmatites here. The red outcrops you can see to the north of the pits G1, G2, and G3. And interestingly, they trend right into the long pit that has the bulk of the uranium at Langer. So to my way of thinking, that's that and the abundance of black quartz is a QED. It's a slam dunk. But how does the uranium get out of the granite? There's no lateritization in this area. To cut a long story short, it's probably fracture controlled. This is a sample of a CT image of a mineralized leucogranite showing very strong relationship between uranium and fractures. So I believe that is how the uranium gets there. In fact, at Rossing, we see that there's evidence of meteoric fluid flow to depths of over 100 meters, and all the uranium at depth is, a significant amount of the uranium at depth is converted to secondary minerals. So I'm running out of time here. I've already exceeded my allotted 40 minutes. So I'll try and hurry through these last few slides, but I want to just try and summarize with a mineral systems model. The architecture clearly is can be expressed as Cenozoic palaeochannels, but we're also looking at fracture zones in basement. Sorry. Fluid reservoir is palaeochannel sediments, which derive their uranium from pegmatites and probably granitoids. An issue that hasn't been addressed is to what extent the uranium is introduced in aqueous form versus how much of it's clastic and then locally redistributed. This is a typical model that's been around since the 70s. Mann and Deutscher were instrumental in developing the initial model for this type of deposit. But what drove the fluid flow? Well, it's probably topography driving meteoric waters into the channel system. except in Namibia, these the hills that formed the topographic drive have long since been eroded away. Deposition, almost certainly due to evaporation, driving brines towards a magnesium-rich and alkaline composition. The way in which uranium is transported in the aqueous form is still not really understood. My suspicion is, given the hypersaline, the likely hypersaline nature of the waters, we're talking about chloride complexes, in which case the pH change may have been a significant driver for precipitation. And if uranium was traveling as chloride complexes, what about other metals? There's plenty of other metals that form stable chloride complexes. Should we be looking in palaeochannels for those too? Finally, in terms of deposition, one thing that's been advocated is that fluid flow was reduced by barriers along the path of the palaeochannel, and that's what this model is showing. We don't see evidence for that in the Urongo district. So the mechanism by which fluid is forced to the surface and evaporates or forced near surface remains uncertain. I believe there's a great need for research to better understand these deposits. Geochronology is crucial. How do uranium deposits fit in with local climatic fluctuations? We need a better understanding of uranium precipitation processes, and particularly an evaluation of how much uranium comes in solution versus how much is transported in clasts. So sorry about the rush at the end. I overran my time a bit, but I hope you found that of use, and I'm happy to answer any questions.